So we're going to continue on now with making observations. You've set up an experiment, you've made a plan, you've defined your variables. What will your independent and dependent variables be? What are some of your control variables? And now you're actually doing the experiment. We'll spend a lot of time during this year in lab experiments, doing experiments, making various tests and seeing what kind of results we can come up with. Sometimes those things will be completely devised from you guys in your imagination. Sometimes they'll be things that I specifically ask you to do in lab in order to see concepts that I need you to experience and see to help you understand the concepts of the class. But when we're doing any lab at all, you want to make sure that you're making good observations and that you're taking the best information down you can, whether it's numbers or smells, colors, volumes, anything at all. You want it to be as good as possible. And so we're going to look at observations and a couple key ideas about those. When we make observations during labs, those eventually lead to interpretations. Those are sort of the beginning of our conclusions and our analysis process. So making good observations is the key. Okay? Observations are any information that you gather with your senses. They can be concrete things that are very black and white. In fact, they should be something that's very unarguable. An observation should be rather clear and well defined. An observation should be black and white. It should not be different from person to person based on their perspective necessarily. Those would be interpretations or inferences, you'll sometimes hear them called. Interpretations can and often are, and we maybe should say should be different from person to person within your lab group, within your class, person to person if you're doing research somewhere in the United States and comparing with someone overseas. Your interpretations of your results should be different. That's often the strength of science, in fact, is that we look at data that's black and white, hard, fast data, and different scientists like yourselves might see different things in that data and draw different conclusions. That sort of wide open freedom to have conversations, discuss things as a science community is what makes science great. So interpretations are the meanings that you take that you make from an observation. Sometimes these are somewhat subjective. There could be multiple different views on this, and even within your own lab group. And again, as we go through the year and you're working on lab reports, handing in labs, don't think that you and your partners always have to agree on everything. Often people get stuck thinking that because my partner believes that it means this, I have to too. Well, stick to your guns. Often it's the minority opinion that turns out to be the right one in the end. We're going to focus for the most part on observations here, and interpretations will come a little bit later. There are basically two kinds of observations, and no matter which of these two types you're working with, you want them to be as good as they can be, high quality. Okay? The first is called a quantitative observation. A quantitative observation is something numerical, something that's got numbers in it based on measurements that you've taken, or sometimes even just approximations that you've taken. These could be things like mass, length, volume, temperature, time, lots of things that as we look at calculations with chemistry, we think about chemistry as being a lot of math. It's because there's a lot of quantitative observations. But there are plenty of the other ones too, and those are called qualitative observations. The qualities of things, not the numbers, not the quantities, but the qualities of those things describe things like color, smell. Does something get warm or cold? Texture of something. Is it a fine crystal or is it a very coarse, kind of large snowflake-looking crystal? Even simply the state of matter. Is it a solid, liquid, gas? That's a qualitative observation. And often people think, as I mentioned in the first video, that those are unimportant things to write down, like a solid was formed. That sounds very plain. Well, write it down. It's something that happened. It was a result, and it's an observation that you made. We should record it, even if it seems something so simple you'll never forget it. You'd be surprised the things that we forget when we don't write them down. So focus on writing down and recording all your observations, whether they be quantitative or qualitative. We're going to spend a little bit of time talking about quantitative, those number-based observations first. Because making measurements is a simple thing, but it needs to be done well. If it's simple, it should be easy to do well, and I think you'll find that it probably is. Quantitative observations, those things that are number-based, temperature, time, volume, all those things that we'll do in chemistry. There's lots of masses, volumes, times, temperatures. They need to be both accurate and precise. Accurate means to be as close as possible to the actual correct value. So for example, if you're measuring the mass of an object that I know is 100 grams, and you come back with a mass of 99.8 grams, that's really good. That's very, very accurate. If you come back with a mass that's 107 grams, maybe that's not so good. So accuracy is simply being as close as possible to the correct actual value that we know is right. The other side of a measurement that's quantitative should be precision, or being precise. So you should be both accurate and precise, or have accuracy and precision. To be precise means to be repeatable. In other words, if you were to make the measurement many times, you would get the same measurement over and over and over again. Or if you would carry out the same experiment many times, you might get the same measurement at the end each time. But it also means something else to us. Each measurement that we take can be precise, and then a series of measurements can also be precise. In this case, a single measurement, when it's precise, means having as many decimal places as the instrument allows. So if you're making a measurement of volume with a graduated cylinder, you should take as many decimal places as possible, as many as are allowed by the instrument. And I'll show you what it means to be allowed, how many decimal places and digits are okay. But you can't take any more than that. You should make as good of a measurement as possible, but not make up quality or precision that really isn't there, because that's just false, and it's sort of more or less lying to the people who are reading your results. But you want to have in a measurement of quantitative type, now an observation that's quantitative, as many decimal places as you can. It's important to know that every tool or instrument has a limit to its precision, whether it's a beaker, a graduated cylinder, a ruler, or a meter stick. It could be a thermometer. Everything has limitations to its quality, to its precision. Generally speaking, the more precise an instrument is, the more expensive it'll be. More precise tools are going to spend a lot more money because it takes finer instrumentation and engineering to make those things come out with that kind of precision. For example, the electronic balances that we'll use in class have 2 decimal places. You can buy electronic balances that have 5 decimal places. We use those in AP chemistry. They have amazing precision. That kind of quality isn't necessary in what we're doing in regular chemistry, plus they're very, very expensive. You can also buy electronic balances that only measure to the nearest single gram, whereas the ones we have in class have 2 decimal places, the hundredth of a gram. And the cost, again, is related to that precision. But again, as I mentioned, you should always record as much precision as possible, no more and no less. You can't make up precision. You can't go through a measurement and just start adding numbers on the end. So for example, if you make a measurement of mass on our electronic balances in class, and the object comes back as 17.51 grams, you can't go back to your lab group and say, it's 17.5147139. You can't make up numbers. That's not permitted. Okay? That electronic balance is only as good as it's made to be. Anything that you make up beyond that is just a bunch of hogwash. It's no good. But you want as much precision as possible. So if that person comes back from the measurement at the graduate electronic balance and doesn't give you as many decimal places as they should, be sure to call them on it. If the measurement isn't as good as it could be, not only will it affect the quality of your results, but in the end it'll limit how you can round your final answer from your calculations too. For non-digital measurements on something like a graduated cylinder or a ruler, a couple quick rules, and then I'll come back in the next video with some examples. First, make sure you set any objects on a flat surface. That's true of a graduated cylinder. You don't want to pick it up and read it in front of you because there's lots of tilting that can go on. A ruler, you don't want to hold things in your hand and measure them. Lay them down on a table to measure them. Make measurements flat. Making measurements at eye level. That's especially now important with a graduated cylinder. You want to hold it up? No, you want to set it down on the desk. And so then reading it at eye level will always mean, pretty much always, getting down and crouching a little bit so that you're looking at it at the eye level. It's really important that you do that. Otherwise, you have that sort of tilt factor built in. Third, you want to read the bottom of the meniscus. And a meniscus is that little curve that water and other liquids make when they're in a graduated cylinder. It's especially strong when you're in a glass graduated cylinder. Plastic, like what we usually use in class, there's not quite as much of a meniscus, but the rule is always to read the bottom of that curve. And lastly, you want to estimate 1 decimal place or digit beyond what is given on the graduations of the tool, of the instrument. And so when you look at the lines on a graduated cylinder, those are going to help you to know how good your measurement can be. And we'll go through plenty of examples in practice on how that's going to look so that you know exactly what I mean by estimating 1 beyond. That's it for now with measurements and observations. The next video we'll come back on will be practicing making measurements on those non-digital devices like a graduated cylinder and how to estimate that digit. Really important skill that you'll learn, I think, rather quickly. We'll see you then.